Afternoon, everyone. Thanks for coming out. Appreciate you coming to join us. My name is Chris. My colleague Till and I are from Salesforce. We're going to talk to you about some work we've been doing on machine learning pipelines and implementing them for a few different applications we're working on at Salesforce. So, what we're going to be getting into today is what kind of data we're dealing with at Salesforce to start with, and then what kind of machine learning we're doing on that data, and then just a brief overview of what we mean when we talk about pipelines, and then the bulk of the talk is Till and I are going to be talking about a few different use cases for these pipelines and things that we're doing with them. One more specific use case that has specially tuned pipelines, and one more generic case that has much more flexible pipelines. So first of all, the data at Salesforce. Salesforce is sort of broken up into different business units we called clouds. They're broken up by function. So the first cloud at Salesforce was the sales cloud. So it has data related to different sales processes, sales leads, accounts, contacts, opportunities. There's a service cloud that deals with service cases. And there's a marketing cloud that deals with marketing, email campaigns, those sorts of things. And there's also a custom type cloud, custom object. So Salesforce is also a developer platform. So outside third-party developers can build applications that work with Salesforce data and store data in Salesforce, and they can develop their own objects and their own schema to store this data. And there's many other different clouds within Salesforce, IoT, analytics, those sorts of things. But the challenge here is all these different clouds, all these different units have different data, different schema, different organization. So we're going to need to figure out a way to get these into our pipeline and deal with all of them. The advantage that we do have, though, is that our data has a rich schema and metadata associated with it. So we're storing our data in a database. It's not just a text field. It's an address field. It's an email field. So we know more information about it. So that allows us to be smart with how we handle it in our pipelines. So we don't have to do a lot of that processing on the front end. The other nice part is we know the relationships between the data as well. So contacts are linked to accounts, which are linked to service cases. And we can do more with that from that perspective as well. Also at Salesforce, we have the notion of multi-tenancy. So Salesforce is a business-to-business company. We deal with hundreds of thousands of different companies that all store their data in Salesforce. But the issue is, every customer wants its own data separate, right? They don't want their data to be going to benefit another customer, potentially a competitor. So we silo every customer's data separately. So all the different customers are going to have self-contained data. And the other thing, about the different customers is they can vary considerably, both in size and scope of the data and dimensionality. So you might have a nonprofit like Kiva, which has a very, very different business process than someone like Comcast or Asana. So there's large differences in the amount, the shape, the scale of the data that we're dealing with. And like I said, we only use a customer's data for their own benefit. So if we're building a machine learning model, we're building it with that customer's data to make predictions on that customer's data. We often use the term medium data at scale rather than big data because all of our data is partitioned not only into different clouds at Salesforce, but different customers, so that we're working with small bits of the data at a time rather than dealing with a big amount of data all at once. So how do we do machine learning with this kind of data? We're developing an internal package we call Optimus Prime, which, among other things, allows us to build pipelines quickly, better, flexible machine learning pipelines. And we can think of it as an improved interface for Spark data frames. So Optimus Prime is an interface to Spark, which of course sits on top of Scala. And our package is, of course, built in Scala as well. So before we get into things too far, let's do a little background on what I mean when I say machine learning pipeline. So typical machine learning pipeline is going to look something like this. You've got your raw data that you probably store in a database in some kind of structured format. You're going to do an ETL step, extract, transform, load, so you get the data out of your database, into some form you can use and get it into memory. In this case, the way we're representing it is going to be in a Spark data frame. It's a vectorization step. So we take all that data that's now in our data frame and convert it into some numerical form, because we're going to take this data and perform some operations with it, and it needs to be in a numerical form. The reason it needs to be numerical is because we're putting it into some statistical modeling techniques. So if we want to do a classification, regression, recommendations, we need that data in the right form. And so with those statistical models, then we're going to use them to produce scores or predictions on any number of things. If it's a classification, for example, will the person unsubscribe or not? If it's a regression, maybe the expected sale price of your product. Recommendations as well. We can predict the most likely to buy or the highest rated item for a particular user. So let's get into the use cases. The first one that I'm going to be talking about is called case classification. So this is a special application of these pipelines. So what do I mean when I say case classification? So this is related to the Service Cloud part of Salesforce, where from a customer service perspective, someone will request some kind of service. So we'll open a service case. So if you're having a problem with your internet, for example, and you email your internet provider and say, hey, I'm having a problem, please fix this, that can come into, if they use Salesforce, that'll come into the Salesforce platform. And now that can be a lot of work to triage all those emails to decide, is this email important? Do I need to address it right away? Can I wait? What's the issue? Who does this problem need to be assigned to so that they can fix it, so that you can do it quickly and effectively? So the problem we want to solve here is, given a whole bunch of history of someone's service cases, can we now predict when new cases come in, what the priority is, what category they're going to be? And beyond that, for each individual customer that's using this product, they may have custom things they want to predict, things that are specific to their business process that exist in their Salesforce data that they might want us to make predictions on as well. So we want to be able to take in any number of different labels, different text, and classify it automatically for them. So what that looks like is something like this. So say you've got an email that comes in, I'm having a problem with my shipment, and it's going to have different tags on it, for example. So this one is classified as medium priority. It was an issue related to shipping. Within that issue of shipping, the specific problem was an address correction. So a customer will have a history of all this data, and this is what we're starting with. So there may be any number of issues, different priorities, different categories, and so on. So these emails come in, someone has triaged them in the past, they've stored this data. So the problem is going to be a multi-class classification problem. It can take any number of different priorities. And it's also going to be multi-field classification, because we're trying to predict these many different fields, the priority, the category, the subcategory in this example. So to do this, we need a more flexible data pipeline, one that can handle all the different customers, all their different data, and handle all the different fields that we want to predict in this case. So what that looks like, you've got your data coming in on the left. We're going to extract out that email field. We'll vectorize it into a numerical form that we're going to call our features. Then you're also going to pull out the field you're trying to predict, the priority field in this case, vectorize it as well. We're going to call that the label. Those both go into our statistical model. And out of the statistical model comes our predictions. Now, we also need to do this for the other fields, the category field, and so on, as many fields as we need to predict. So this is the overview of the pipeline we're trying to create here. Now, each customer is going to need a different pipeline, obviously. So, say Asana wants us to predict what the priority, the category, and the subcategory are going to be from emails. Kiva might want totally different fields. Comcast has a lot of stuff they need to predict. So we want to be able to scale our pipeline up and down to be able to train all these models and make the predictions that are requested for any customer that's looking for them. So what does that look like? How do we generate this pipeline? So here's inside the feature vectorization that we're working with. So you get an email that comes in. It's a bunch of text. So in Spark, if we want to deal with that, we can load up a data frame. So you load up that data into a data frame. But we take a different approach with our package at Salesforce. Rather than dealing with a data frame directly, we think in terms of the features that we're creating. So instead of loading the entire data frame, we're going to extract that email feature out. And we have a notion of a feature builder that does that. Some of the interesting parts of it here, first of all, like I said, it's a feature, not a data frame type that we're dealing with. And we have a statically typed feature, so we're extracting a feature of type text. And we also have statically typed sources. So this is coming from a case object. So because we know those things, we know a considerable amount about the structure, the schema, the sorts of things, and different transformations that we can do with them. So the next step in our pipeline, we'd want to tokenize that data. So you'd split up that blob of email text into different words. And you can do that in Spark. There's a notion of a tokenizer. The tokenizer does that. You set your input column and your output column in the data frame, and you're good to go. It will handle it. The way that looks in Optimus Prime, we've got an email.tokenize method built into our features. So our input and output features are implicit here, so we don't need to specify those specifically. And because we know the types of these, we can do a typed transformation. So that email is a text field, and we know a lot of times on text fields you're going to want to tokenize them, so they have a tokenize method as well. So this, the same things are happening on the back end, but we have a simpler interface for them. So there are a few other things you might want to do in your pipeline. After you tokenize it, you might want to remove the stop words. So those are common English words that might just add noise to your model. And Spark has a stop words removal. So again, a stop words remover. So again, you can specify it like this. You set an input column and an output column. Something else you might want to do is lemmatization, where you reduce words to a common root. So for example, having, have, had will all be replaced by the same root word, again, to reduce noise in the many different versions of the same word. There's no version of this. There's no lemmatization package in Spark, but you can do this from an external package if you import this. But we can accomplish all of this in a single step in Optimus Prime, again, because it's a common transformation. One way to do this is in our tokenize method, you can specify a default language. So if we know that it's English, we can remove the common English words. We can do the common English lemmatization. And then the last step that we would want to do in our feature pipeline is to actually create a numerical vector to go into our statistical model. So in Spark, there's this hashing transformer, which hashes each word into a bin. You set the number of features. So you set a couple parameters on it. And again, input and output column. And then the way that would look like in Optimus Prime, again, the first step is to do the lemmatization. And then we have a vectorized method that applies to that. So after it's lemmatized, that returns a feature of type text list. So it's a list of strings, basically. And because we know it's a list of strings, we can vectorize that as well. And we've got the same thing going on in the back end, the hashing transformer. So we specify the same parameters, but again, it's more concise and type-safe syntax. And if you want to use a different vectorization method, for example, TF, term frequency, TF IDF, those are available as well. So let's get into the modeling step next. So the way a model works in Spark, you'll give it features and a label, and it will return a prediction, a probability, and a raw probability column. So these are what will eventually turn into our predictions. And that can be specified in Spark like this. You have a logistic regression model. You set the input and output columns, and you can set your parameters for that model. One thing that's not specified in here is where your outputs go. So it's inherent in each different model what outputs come out. So logistic regression will produce these 3 columns for your data frame with these names. And that's implied, and it's not explicitly controlled here. In Optimus Prime, this is what it looks like. So we take that feature vector we created. This will now have a logistic regression method we can apply to it. And then we specify the label column associated with it, and we specify the parameters. So we're again specifying the same things, except now our outputs are going to be these 3 new features: a prediction, the raw probability, and the probability. Now, say we want to take that a step further. Instead of training a single model, it's typical that you want to do cross-validation and train models with an array of different parameters. You can do that in Spark. There's a param grid cross-validation. You set the array of parameters that you want to use, and it will iterate through them and choose the best one based on a certain evaluation method. In Optimus Prime, we also have a built-in method for doing that. It's the same logistic regression method, except now we can specify our regularization param as a sequence instead of a single value, and it will do the exact same thing on the back end. So a step beyond that, say we want to train multiple statistical models in Spark. So not only logistic regression, we want to try a random forest, decision tree, a naive Bayes model. In Spark, that becomes really challenging. Each of those algorithms has different outputs, and they don't always blend together, and it's not so easy to do that kind of model selection. But we have built that into Optimus Prime. So we have a generic classify method that will test all available models for classification in the package with default parameters in a much more concise syntax. And lastly, say we want to combine all this together. We want to train multiple models. We want to do different parameters for each model in a huge parameter grid, and we want to pick the absolute best model for a particular customer for their particular data. That gets really, really hard in Spark. So to do that in Optimus Prime, it gets long, but we can specify, again, a sequence of all the different parameters we want to try for each model within this classify method. And what it will do, it'll iterate through each model, through each combination of parameters, and pick the very best one in performance in terms of their cross-validation. So what does that whole pipeline look like in code if we want to make it flexible? So if we want to predict many different fields, we can start with the sequence of those fields we want to predict. We're going to want to predict a priority, a category, a subcategory field for this particular tenant. So next step is to create a sequence of features. So that's just going to be a simple map operation. We're going to apply that feature builder to each of the different features and extract them all out. So now we have a sequence of labels, of features. And the next step with those labels is we want to classify them. We want to train a different machine learning model on each set of labels and features. So again, we can apply another map operation and do a classification for each of those different fields. So now we can specify which models we want to train, what parameters we want to try. For each field, for each customer, we'll pick the absolute best one. So again, we see that scalable pipeline. It's as simple as passing in a different sequence of fields to predict for each customer. So what are the things we have done to make this easier in Optimus Prime? We treat features as a first-class citizen. So the developer is working directly with the features, not the data frames. The dependencies, the inputs and outputs are handled automatically, and it's going to be much simpler to iterate. We use a functional syntax now, so that makes it reusable, maintainable. All the benefits you get of using a functional syntax, you get here. We can do model selection over a much broader range of models, much broader range of parameters. So that allows us to dial in to the most accurate model we can get for the particular situation. And lastly, we have type safety. So in Spark, you're dealing with columns and with the string name of the column when you want to extract them. But with type-safe features, now we're able to catch issues at compile time rather than runtime in the middle of a giant job. You can get the other bonuses like code completion in your IDE and those sorts of things that make development a lot faster and more accurate. So up next, I'm going to hand things over to Till, who's going to talk to you about a more general pipeline that we've been.
All right. Yeah, hey everyone. So Chris has shown you how to kind of like use Optimus Prime to build a pipeline for one specific use case, which will work great for that use case, but obviously not for any other use cases. And that's the whole point of it. But as you remember, there's a lot of different use cases. There's a lot of different clouds, a lot of different schemas. And the problem is because they can also be custom. Like every customer in Salesforce can create their own custom objects, and they do, a lot of them. And we just simply, there's not enough data scientists at Salesforce or anywhere really that we can go in and for every single schema can have one of those specific pipelines. There's just not enough time. And for data scientists, and this is pretty obvious, a lot of these problems, these common use cases of what customers want to do boil down to two different things. They're either classifications. For example, you want to analyze churn and attrition, or some kind of conversion from one status to a different status, or the other big part is regression, where you have a number field and you want to predict this number. For example, the revenue in the next year, the number of days until something happens. So for example, until a bill is actually being paid, so you can calculate how much money will you have at the end of the month. And I can show you quickly, hopefully, because this is a live demo, how a customer right now in Salesforce would actually solve this problem for themselves if they want to build a classification. So, okay. So here you can see this is actually how Salesforce looks like. You have a bunch of different objects. These are the different rows. These are called contacts. And let's say for each of those contacts, you want to analyze, well, how likely is it that this customer attrits and stops being a customer in some time frame? So all you have to do right now is just use this Einstein prediction builder. You make a new prediction. You give it some name. So just cool demo. You choose the object that you want to predict. So there's a lot of objects usually in Salesforce. So you use the contact object here for this use case. You simply select the field for which you want the prediction. Here we want to predict if someone attrits. So there's a field called attrited, which is just a formula basically of true and false. And you can then use all your fields that you have in all the data fields that you have in there. You can use that to actually build your prediction, use it as features. Usually this kind of like field is around 500 fields or something. It's a lot longer. And obviously you want somewhere to store this prediction. So you can just choose a field where the probability then gets fed back. And this is all that you have to do to kind of like create this custom prediction for your use case. So let me show you how that actually, what actually happens when we build this prediction. So each of this, after this UI, or like what we kind of need to build this pipeline for these custom generic use cases is we need to know about which field to predict, which fields to use as features, and what the data types are. And as you've seen in the UI, we already get that from the UI. And the types we get from the rich metadata that Chris was showing earlier. We know whether it's an email field. We know whether it's a pick list, whether it's a string, and that kind of stuff. So this is just simply how we store this configuration. It's very simple. We just have a response where we have the field and the type. In this case, it's attrited is the field, type is Boolean. And then we have a list of fields that we want to use as the predictors. So here's a couple of examples, and this would usually go on for like a couple of lanes. And this is all we need to know to build these predictions for any kind of use case. And so Chris really went into kind of like a deep look into like how we build these transformers and how we kind of like transform the features. And that's possible because he knows, well, he's going to work on the case object. He knows all these fields exist. We don't really know what type, what actually these fields have, what kind of information they store. We only know one thing, and that is their type. So for example, when we know there's an email type, so we might want to extract the domains. So maybe what kind of company they belong to, what the @ sign is, right? And then we want to pivot and keep the top K, maybe the top 10, the top 20 common occurrences of that domain. And then we need to also vectorize it. So we need to do all these single steps. But if you have a pick list, a categorical value, you don't want to extract anything. You just want to keep the top K and then also vectorize it. If you have a phone, you might want to check, well, is this a valid phone number or is it invalid? What's the area code? All of those things you can do. And then again, you need to put it into a vector. If it's numeric, you can do multiple things. You can normalize it, put it into a vector. You can bin it, and then put it into a vector. And this goes on for all of the different Salesforce types that we have, which are around like 20 or 30 types. So if you want to do this for every single field that we get from these customers, which is hundreds of fields, we would probably never finish writing the code because it's just too much work. And for a company like Salesforce, where we have unknown kind of like data entry practices from the customer, they don't tell us how they actually collect this data. One really useful thing for us is also for all of these features, we want an indicator whether that field was null or not. And the magic of kind of like Optimus Prime here is that we can simply just call one function to do all of this, and that is just called .vectorize on it. And it does all of the things that I described for all of the different fields. The problem with this is that now we have not only like hundreds of fields, the hundreds of fields magically turn into hundreds and hundreds of features. Because if you pivot, for example, into top 10 domains, you suddenly don't have like one column, you have 10 columns. And there's multiple problems with this. Well, a lot of these might just provide you with no information gain in the model. It's not going to harm your model, but it might slow down your model building a lot. So there might be really low correlation between your feature and the outcome. The field might actually be the same for all rows, so it doesn't carry any information. And you want to throw that out as soon as possible because it just slows down your model building. Another problem, which is way bigger, is if you remember this feature list that I showed you, there's a field in here called attrited date. Now, we're trying to predict if someone is attrited or not. That field, attrited date, is not going to be filled out if that person hasn't attrited yet, which is a huge problem because our model, math, even though it's math, it's kind of dumb, and it will just, there's a perfect correlation. It will just use that field to predict whether someone is attrited or not, which is not really helpful because when we give the predictions, that field is always going to be null. So this is called label leakage, and we definitely want to catch that because that is actually harming our model. Our model will not really perform well. So this is a lot of work. If you're a data scientist, you spend hours and hours trying to catch all of these label leakage things. You try to really optimize all of your features. Using Optimus Prime, you just have to call one function again, which is .sanity check, which is what we call this sanity checking and feature selection. And to quickly show you what the whole pipeline actually looks like for this generic problem, it's really only 3 functions. All that you have to do is call .vectorize on a sequence of raw features, which will automatically pick the best transformer, creates the best features for your field type. You have to sanity check it, which is just simply one function again. And then you call .classify if it's a classification problem. And if it's a regression problem, you just switch out .classify for regression. So just to kind of like iterate, or just to summarize again why Optimus Prime makes these complex pipelines really accessible and easy, is Chris has shown that for streamlined pipeline creation for one specific use case, you can use it to build these really in-depth pipelines really well and easily, way easier than in Spec. But also, which is really helpful for developing, you have this AutoML functions, which you can use for these flexible pipelines. So for any use case that you really want to throw at it, it's really easy to get started and develop really good models. So you have smart feature transformations based on types. You have the sanity checker and the feature selection, which gets rid of unnecessary and harmful features. And you have the easy model selection, which will just do cross-validation and run different kinds of algorithms on your data without you having to specify any of them. Or to summarize, it makes complex machine learning pipelines easy. And that was it. Thank you. Yeah, I think we have time for questions.
So for the sanity check, I assume the data leakage check is just too high a correlation between column X and the field you're trying to predict. How do you do like the not so useful feature pruning?
So this with the not so useful things, there's multiple things that we do. So we also check for low correlation. If the correlation is very close to 0, you can also remove it relatively safely. The other thing is also that in our model selection, you use pretty high regularization in the logistic regression or something, so you'll still have the feature in there. It'll just won't be used in the model. Yeah. And also, like I mentioned, low variance, right? If it's the same value for all fields, and the variance is really low, it also gets removed. Yes, for all rows, right? If you have 100 rows and the country is the same for all of them, then it doesn't really carry any information. Yeah. Any other questions? Way too quick.
So I want to refer to regression problems. Do you also monitor outliers and noise, for example? So you get rid of outliers from data sets so they don't skew the result?
So yes, so it's a good question. With outliers, so we try to get rid of them we try to catch them in the sanity check already, right? With like correlation, we also do, for categorical features, we also do Kramer's V to kind of like, see what the correlation there is between the features. I think if we do regression, nothing happens if there are outliers as such, but we usually try, when we actually, we do sometimes look at the models. It's not completely hands-off, but pretty hands-off. We try to see why, if there are outliers, why those are caused. And usually the way we do it is, we look at them, and usually the outliers happen because there's some kind of data entry error or something, and then we can kind of like feed that back to the customer too. Yeah.
How did you come up with the name Optimus Prime?
I don't know how we came up with that. No, I don't. So it's because it's essentially a series of transformers. Yes. We might have to change the name for legal reasons at some point. So yeah, watch out for a different name soon.
So I understand you're going to possibly open source it. You've gone through a pilot for this, so what are the barriers to that?
The name. No, so I think we are currently in the process of kind of looking for outside customers who are interested in using Optimus Prime. If you are interested, or anyone is interested, I can refer you to the right person to talk to, which is not me. And yeah, the plan definitely is for this to be open sourced at some point, but I don't know what the timeline is. But as I said, if you're interested, come and talk to me, and I can point you to the right person to talk to. Any other questions? Sorry, I've been hogging the mic. But you were. Okay. Cool.
All right, thank you, everyone.
Thank you. Why are we so quick?